All right, here we go. This is the Unit 1 Trig Final Exam Review, Unit 1, Page 2. Yeah, lots of stuff going on there. All right. They want us to find all 6 trig ratios here. So the first ones, right, we know are going to be your SOHCAHTOA. All right, and again, this is something that we talked about in geometry, and then we introduced 3 more. We have these 3 over here, your cosecant, your secant, and your cotangent. And if you wanted to think about those, we know the sine, we said, is equal to the opposite over the hypotenuse. And then we said, well, we have these things called reciprocals, and those are the same kind of things, but what we do is we flip the ratios upside down. So the cosecant is the hypotenuse over the opposite. All right, and we have 3 of them. So the cosine, of course, the cosine is the adjacent over the hypotenuse. So the reciprocal of that one we call the secant. Right? And the secant is just the hypotenuse divided by the adjacent. And then the very last one, of course, is the tangent. All right, the tangent function is the opposite over the adjacent. So the reciprocal of tangent is your cotangent, which is your adjacent over your opposite. So those are the 3 ratios that we are dealing with in this section. So the first thing we need, the first thing I noticed that we are missing is this piece right here. So in order to get that, we need to do the Pythagorean theorem. So I'm just going to go ahead and call this like x or something, right? We know that, what do we know? We know 3 squared plus x squared equals 4 squared. So we have 9 plus x squared equals 16. Subtract the 9 over x squared is going to give us a 7. Thus, x equals the square root of 7. I should put a plus or minus there, but for the time being, I'm going to leave it as the positive. We'll get into the plus or minus thing a little bit later on. So this piece right here is equal to the square root of 7. Now, here is our theta, right? This kind of dictates everything. So this is our hypotenuse. The 4 is the hypotenuse. The square root of 7 is your opposite because it's across from that theta. So that means the 3 is the adjacent. I always save the adjacent for last. I don't know why, I just do. All right. So to write out all of these fractions. Now, unfortunately, on these, we have that radical on the bottom, which is always, unfortunate. So the sine here is 4 over the square root of 7. Now, we don't like having that radical on the bottom. So in the last video, we talked about rationalizing denominators. I'm not going to go through that whole process on all of these because I'm trying to make this video somewhat short. So this ends up being 4 squared of 7 over 7. That's the rationalized denominator. The cosecant, what I'm going to do is I'm going to look at the original. All right, I'm going to flip that one around. This is the square root of 7 over 4. That way it's already rationalized. If I were to look at this one and flip it upside down, I would have to re-rationalize it, and that's just going to save, it's going to take too long. So we're trying to be efficient here, all right? So you're going to take that fraction, flip it upside down, and there's your reciprocal function, right? That's your cosecant. Now the cosine is going to be, what do we have here? The adjacent over the hypotenuse, so 3 over radical 7. So rationalizing that, we get 3 radical 7 over normal 7. And again, flipping the original cosine upside down, we're going to get radical 7 or square root of 7. I kind of interchange those over 3. Then the last one, the tangent, we have the square root of 7 over 3, right? So the reciprocal of that is 3 over square root of 7, and that does need rationalizing. You only rationalize it when the square root is in the denominator. All right, and that's going to become important later on for the unit circle. So this is 3 root 7 over 7. All right, and there we have it. Right, did I do that correctly? I think I did. Let's see here, opposite over adjacent. Huh. Okay. Well, there we have it. How many degrees does the hour hand on a clock move from 6 a.m. until 10:30 a.m.? So 6 a.m. is, I'm going to just draw. I know the hour hand is the short one, but I'm just going to do that. All right, 6 a.m. until 10:30 a.m. That is going to be right here. How many degrees is that? All right. Well, how can we do this one? So how many degrees is that? We know a whole circle is 360 degrees, and one full rotation here is 12 hours. So if we just think about this proportionally, 12 hours is equal to 360 degrees. All right. Well, how many hours have we moved? We're going from 6 to 7 to 8 to 9 to 10 to 10 and a half. So that is 4.5. So 4.5 hours is equal to something. So here you go, little throwback to algebra again. We're going to say 12 over 4.5 equals 360 degrees over x. That's a proportion we can solve, cross multiply, all that good stuff. I'm going to go over here to save some room. 12x equals, I don't know what that is, 1620. All right, divide both sides by a 12, and we're going to get 135. All right, but I need to mention something because this is moving counterclockwise. What we have done, what mathematicians have done is we said that any, see, what am I doing? It's moving clockwise, not counterclockwise. Of course. Let me start over. All right, we're going clockwise. Mathematicians way long ago, thousands of years ago when clocks were first invented, we said that a clockwise angle is going clockwise angle is going to be defined as a negative degree. All right. So the correct answer, the final answer here is negative 135 degrees. All right, all clockwise motion is a negative angle. Counterclockwise is a positive angle. Why do we do that? I don't know. That's one of the most annoying things about math, in my opinion. It drives me crazy, but that's just something that we have to accept. All right, so clockwise angles are negative. Counterclockwise angles are positive. All right. Next one. Find the value for x. This one really doesn't have much to do with trig. This is the Pythagorean theorem. We use that all the time this year. X squared plus 12 squared, right? The leg squared plus the other leg squared is equal to the hypotenuse squared. All right, in a problem like this, the most common mistake I see is on the right-hand side of this problem. This x plus 8 squared. You have to remember, what does a square mean? Well, a square means multiply by itself. So x plus 8 squared turns into x plus 8 times x plus 8. All right. So if you call that x squared plus 64 and you simplify that way, that's wrong, right? Because this turns into a double distribute problem. This x has to go to both terms, and this 8 has to go to both terms. All right. So the left side, that doesn't change at all. We have x squared plus 144. That's fine. All right. But the right-hand side of this equation is going to turn into this. X squared, x times x is x squared, x times 8 is 8x. The two middle terms, you have 8 times x, which is another 8x. And then the last one is your 8 times 8. There's your 64. Right? So double distribute on this problem. That is important. So we're going to have x squared, combine your like terms, 16x's now, plus 64, right? And you'll notice, hey, those x squares cancel, right? You subtract them on both sides. I'm going to combine some like terms here. So we got 144 minus 64. That gives us 80. So we know 80 equals 16x, right? What is 80 divided by 16? I think it's 5. It is. Right? So x equals 5. All right, and there we have it. Let's see here. Write each expression in terms of their co-functions. So one thing to kind of recap on this one, co-functions. All right, so cosine and sine are co-functions. What does that mean? That means their angles are supplementary, right? So for example, the cosine of theta, any angle you want between 0 and 90, all right, is going to be equal to the sine of 90 minus that angle. All right, so for example, the cosine of 1 is equal to the sine of 99 minus 199. It's on a roll too. 90 minus 1, which is 89. All right, so if you want me to prove that, which it wouldn't be a math class if I wasn't proving something, let's just confirm that. The cosine of 1 degree, it's going to be some decimal, right? Probably small. All right, so 0.999847. If I type in the sine of 89, I'm going to get that same exact decimal, right? One more to mention is tangent. Tangent and cotangent are co-functions. All right, so the same thing is going to apply here. So the tangent of theta is equal to the cotangent of 90 minus theta. Right, so I can do the same thing. The tangent of 1 is equal to the cotangent of 89. Right, so what they're saying is, hey, just identify the co-function here. So this one is equal to the sine of 90 minus 72, which of course is going to leave us with an 18. All right, so the co-function, cosine, is the sine of 18. All right, and that comes in handy every now and again, like we're working with triangles. Now this next one, we have to be careful. All right, this one is the tangent, not the tangent, it's the cotangent. The cotangent of 90, right, 90 degrees. I'm using a bracket this time instead. I don't know why. Well, I do know why. So we have parentheses inside of parentheses. Brackets and parentheses kind of mean the same thing in this context. It's just an organizational thing, personal preference, really. All right, but anyways, this whole thing, all right, this 2x plus 20, this is your theta. All right, so basically I'm saying 90 minus theta. I want to subtract both the 2x and the 28. If I leave off those parentheses, that's going to make me combine my like terms incorrectly. So that's just something to keep in mind here, because this is going to be the cotangent of 90 minus 2x minus 28. If I forget those parentheses, I'm going to leave off that minus 28. I probably keep it as a plus 28. And now when we combine our like terms here, I'm going to say the cotangent of 90 minus 28. I think it's 62. is 62 minus 2x. Right, so that is our answer here. So the cotangent, I did all capitals, I don't know why. Let's fix it. The cotangent of 62 minus 2x. All right, so theta, x, y, z, whatever, it's a variable. Okay, so there you go. Just something to kind of be careful of on this one. Now they want us to find the value of x that makes the following co-function statement true. I left this one off the previous page. I kind of forgot about it, but sine and cosine go together, cotangent and tangent go together, secant and cosecant go together. So the secant of theta is equal to the cosecant of 90 minus theta. All right, so what's going to make these two things true? All right, if we set these two things equal to each other, that's incorrect. All right, so we're going to have to throw that 90 minus in there somewhere. Doesn't really matter which side you put it on. So here's what I'm going to do. I'm going to say 2x plus 5 is equal to 90 minus the cosecant side. So we have 3x plus 15. All right, so in solving that, what are we going to have? 2x plus 5 equals 90. Distribute the minus sign in. We got minus 3x minus 15, and then clean it up a little bit. I'm going to add 3x to both sides. You got a 5x equals, I'm going to subtract the 5 from both sides. That's going to be 5x equals 70. And then x is going to equal 14. So if I plug that in, if I wanted to confirm this, right, we'd say the secant of 2x plus 5 is 14 times 2, 28 plus 5 is going to give us 33. All right. Now on the other side, that is going to be the cosecant of 14 times 3, 42 plus 15 is 57. All right. If you want to check yourself, right, just add them up, see what you get. 33 plus 57, that equals 90, all right, which is what we wanted. Right. And again, if you're still not convinced, throw them in your calculator. So the secant is the reciprocal of cosine, so I'm going to say 1 over the cosine of 33. All right, that's going to be some ugly decimal, 1.19. The cosecant is 1 over sine, so I'm going to say 1 divided by the sine of 57. Right? That should give us the same decimal, which it does. Right? So there you have it. That is your recap of co-functions. Look at that. Just like that, Unit 1 is finished. That is 1/7 of our course. All right, we'll see you guys in the next video.